All right, let's just jump right in. Welcome to The Explainer. Today we're unpacking something that's probably sitting in your house right now, totally ignored. It seems completely mundane, but honestly, it is secretly fascinating. We are talking about the electric water heater. You know, the geyser. It's basically just a heavy metal tank full of water doing its thing in the background day in and day out. But underneath that plain exterior is a hidden, literal hazard and a ridiculously brilliant piece of engineering actively working to keep you safe.
Which naturally brings up a pretty dramatic question. What actually stops your water heater from exploding? Now, I know that sounds intense, but think about what a geyser actually is when you strip away the outer casing. It's essentially a massive tank of water held under constant municipal line pressure, right? And we're just constantly blasting it with high wattage resistive heating to warm it up. If left totally unchecked, that water wouldn't just get pleasantly warm for your morning shower. It would rapidly blow right past its atmospheric boiling point.
And our source material for today does not mince words about the stakes here. It explicitly warns of a, quote, catastrophic pressure vessel explosion. I mean, yikes. Without an automated control system to regulate all that massive energy input, all that boiling water would just flash into high-pressure steam, and that steam would build and build until it literally bursts the structural seams of the tank. It would turn a boring household appliance into a literal bomb right inside your house. So how exactly do we prevent this terrifying scenario? Well, the source document we're digging into today actually maps this out beautifully. It details the incredibly clever engineering tucked inside the electric geyser thermostat. And what's really truly fascinating here is that the solution to this incredibly dangerous problem isn't some complex digital computer. It's not a fragile piece of software that needs a reboot. As the text outlines, it all comes down to differential thermal expansion and mechanical snap action loops. It is a 100% solid-state solution.
The big takeaway here is that this unseen hero relies on a purely mechanical, robust safety loop. And the absolute best part of this engineering? It requires absolutely no external electrical power whatsoever to measure and manage the temperature inside the tank. Think about why that's absolutely crucial. If your home's electrical grid surges or your digital smart home systems totally crash, this physical mechanism still works perfectly. It keeps the temperature regulated and it keeps you safe from, a pressure explosion.
So you might be wondering, how does a purely physical system actually know when the water is too hot without using any electronic sensors? Well, it all starts with a foundational physics concept, the coefficient of thermal expansion, or CTE. In simple, everyday terms, this is just the physical principle that governs how the size of an object changes when you change its temperature. Different materials react totally differently to heat. Some expand a whole lot when they get hot, while others, they barely change their shape at all.
Now, what's so cool is how engineers harness that CTE principle to create what the source calls a composite bimetallic element. They basically take two very specific, highly contrasting metals. On one side, we've got the high expansion active layer. This is usually made of brass or a copper-nickel alloy, which is super sensitive to thermal changes and expands really rapidly when heated. But on the flip side, we have the low expansion passive layer. This is made of Invar, a nickel-iron alloy which has almost zero-dimensional variation under thermal load. So basically, when things get hot, the active side is trying to stretch way out, while the passive Invar side just sits there, barely moving an inch.
But here's the kicker. These metals aren't just sitting side by side. The real magic happens through mechanical bonding. These two vastly different metal sheets are cold-rolled together or permanently fused with absolute structural rigidity right along their interface. They are forced to behave as a single dual-property strip. They are physically trapped together, and that sets up a massive internal conflict the very second the water around them starts to heat up.
Let's walk through exactly how this plays out, what our document officially calls thermodynamic distortion kinematics. Step 1, the temperature in the geyser climbs. Step 2, that high expansion brass tries to expand and take up more volume. But because of that permanent bond we just talked about, it can't simply slide forward. It's completely locked in by the unmoving Invar. So something has to give, right? Step 3, the tension just becomes way too much, and the entire composite strip is forced to buckle and bend into an arc. The heat is literally forcing this solid piece of metal to curl up. But wait, actually, we've got a new problem. A simple, slow bend as the water gradually heats up isn't actually enough to safely kill the power to the heater. Why? Because the danger of a slow bend is the potential for electrical arcing. Dangerous, slow arcing across a gradually moving gap. If the metal strip just sort of lazily curled away from the electrical contact to shut off the power, the electricity could literally jump that tiny gap. That creates a continuous, super hot spark, an arc, that would fry the thermostat entirely and completely fail to stop the water from boiling.
So the engineers had to figure out a way to make that physical break instant. And that brings us to a really critical number.
As the water heats up, the strip bends and bends, building up immense mechanical tension. The target temperature threshold, the absolute critical deflection point inside the tank, is typically set right between 60 and 70 degrees Celsius. The strip is specifically engineered with an internal curvature to hold its ground, resisting the urge to break the circuit right up until that specific temperature window is hit.
And this brings us to the absolutely ingenious resolution of this whole thermodynamic process. To prevent that dangerous electrical arc we talked about, the bimetallic strip is hooked up to a spring-loaded over-center mechanism. Once the strip bends past that critical 60 to 70 degree deflection point, snap! The internal spring instantly snaps the electrical contact points completely apart in a matter of milliseconds. It doesn't slowly pull away, it violently, cleanly breaks the circuit loop. This instantly kills the power of those heavy heating elements long before the water can ever overpressurize and cause that catastrophic explosion.
It's just an incredibly elegant solution, isn't it? A purely mechanical snap that saves our lives and our homes every single day, just hiding right there in the utility closet. Which leaves us with a pretty fascinating final thought for you to ponder. If a tiny, brilliant piece of expanding metal in a spring is doing all of this heavy lifting to prevent a literal household disaster, what other purely mechanical systems are silently keeping you safe every single day? Definitely something to think about the next time you turn on the hot water. Thanks so much for joining me on this explainer.